Hi everyone, welcome to my YouTube channel. In this video, I am going to explain you about Maxwell's thermodynamic relations using thermodynamic potentials. Before going to start, if you are new to my channel, please subscribe my channel for upcoming videos. So let us start. So this is the topic from thermodynamics. So this is very important as per your CSR net exam or KSET exam. So many of the questions are going to come from this. So first you need to understand the thermodynamic potentials and then Maxwell's thermodynamic relation. So thermodynamic potentials, there are four functions that are analogous to the potential energy, which are here U, H, F and G. U stands for internal energy, H is enthalpy, F is Helmholtz free energy and G is Gibbs free energy. So these four functions play role similar to the potential energy. That's why we call them as thermodynamic potentials. So which are similar to the potential energy for a mechanical system. So that's why we call thermodynamic potentials. So which have the minimum values for stable state. So here once we understand these four functions, nothing but the four potential, then we can derive the thermodynamic Maxwell's relations. So the change in internal energy, free energy, Helmholtz free enthalpy and Gibbs energy during an infinitesimal change, which are given by these equations. These are what change in these four functions. So du, internal energy, is given by T ds minus P dV. So enthalpy T ds plus V dP. And free energy, Helmholtz free energy, minus P dV minus S dt. So Gibbs free energy V dP minus S dt. So here we have to note down these variables. Here on the RHS side of these equations are related to pressure, volume, entropy and temperature. Okay, so here this is what RHS side of these four equations are related to pressure, volume, entropy and temperature. So the first relation, thermodynamic relation for Maxwell, we should understand using internal energy. So internal energy or intrinsic energy. So here if you want to derive this equation, let us consider here dq be the amount of heat energy absorbed by the system and the work done, that is dw is equal to p into dv, be the amount of work done by the system in going from that is initial state to final state. Okay, then change in internal energy of the system is given by du is equal to dq minus dw. Okay, here dq is equal to what? T ds and dw p dv. That is for the amount of heat absorbed and work done. So the difference between these is what? Internal energy. So dq you can just replace with TDS and dw work done P into pressure into differential of volume. So the differential the internal energy U with respect to the variables volume and entropy. So internal energy, that is for partial derivative dou U by dou Vs. Here this, after getting this equation, if we take the partial derivative of internal energy with respect to volume, okay, here the first, Then this term is going to be what? Equal to pressure minus P here. So minus P is equal to dou U by dou V at constant entropy. If this entropy is 0 or constant, then we can write here dou U by dV. Dou V at constant entropy is equal to pressure, negative of the pressure. So similarly, if this volume is constant, then equation for the internal energy in terms of temperature we can write dou U by dou S at constant volume, that is equal to T. So first we need to write the internal energy in the form of differential form. Then we can take the partial derivative of internal energy. Then we can get the equation for pressure and temperature at constant entropy and constant volume. So after getting internal energy is what? Perfect differential. So we can write here. So whatever the constant we have written here, we can take here dou by dou S. Here entropy is constant in this equation. So just we can equate here these two equation, and finally we can write here the first Maxwell thermodynamic relation we can obtain with the help of internal energy or intrinsic energy, that is dou P by dou S at constant volume is equal to minus dou T by dou V volume at constant entropy. Okay, so this is what Maxwell's first thermodynamic relation that we obtained from internal energy. Okay, next similarly the second equation, Helmholtz function. So the Helmholtz function is given by the difference between internal energy and the product of temperature into entropy. So once we write this equation for Helmholtz free energy, just we should write it in differential form. dF is equal to du minus T ds. We have to differentiate T and S. So T ds minus S dt. Okay. Here we can write this as dou U minus T ds. And here minus S dt is there. So from these three, just we can keep TDS. Once again we can just write internal energy equation, that is TDS minus PdV from this previous equation. Okay, see this second equation. Then we can replace here internal energy in this Helmholtz function differential form. Then we can see here these two terms get cancelled. So remaining what? Minus PdV minus SDT. So again we have to take the partial derivative of Helmholtz function with respect to constant temperature and volume. Okay, so here in this first term dV minus PdV, that is we will get the equation for pressure at constant temperature. If temperature is constant, then we can have this equation for pressure, that is negative. So similarly, if volume is constant, then we can have the equation for entropy here. Okay, so these, after getting these equations, as we know the perfect differential form of F we can write. Then using these equations we can just write the second Maxwell thermodynamic relation, that is dou S by dou V at constant temperature is equal to dou P by dou T at constant volume. Okay. So the first Maxwell thermodynamic relation is dou P by dou S at constant volume minus dou T by dou V constant entropy. So the next third one is related to enthalpy. So enthalpy of the system is given by the sum of internal energy plus product of pressure and volume. So the enthalpy is what we can take the differential form internal energy plus PdV and minus VdP. So internal energy equation we know, so we can substitute that and we will have this equation. Here these two terms get cancelled. Okay, remaining is what? TdS plus VdP. So this is for enthalpy. Then we can take the partial derivative with respect to S sin P, okay, at constant entropy and pressure. So we will get the these two equations, dou H by dou S at constant pressure is equal to temperature, dou H by dou P at constant entropy is equal to volume. Then these, since this differential form of H is perfect differential, therefore we can write these, equate these two equations. Finally we will get the third Maxwell's thermodynamic relation, that is dou V by dou S at constant pressure is equal to dou T by dou P at constant entropy. So the fourth thermodynamic Maxwell's relation, that is Gibbs function, using Gibbs function, that is given by enthalpy minus T into S, temperature into entropy. So enthalpy is what? Sum of internal energy into product of pressure and volume. So we should write differential form of Gibbs free energy. So once we differentiate, we will get this equation. Okay, then you can just substitute the internal energy equation here. Once you substitute, you are going to get the final equation for differential equation, that is V dP minus S dt. Okay, then partial differential of Gibbs free energy with respect to here pressure and temperature we have to take. Okay, once we write the partial differential equations, so here dou G by dou P at constant temperature is equal to volume, dou G by dou T at constant pressure is equal to negative of the entropy. So here Gibbs free energy is the this dG is what? Perfect differential. So once we write these two equations, then we can have the fourth thermodynamic relation, that is dou V by dou T at constant pressure is equal to minus dou S by dou P at constant temperature. This is the fourth Maxwell's thermodynamic relation. So here we have derived the four Maxwell's thermodynamic relation, and these equations are very important as per your exam. Many questions are going to be from this topic, so you should remember all these four equations. So first one is what? First Maxwell thermodynamic relation is with respect to internal energy. So this is the first thermodynamic relation. Then second, with using Helmholtz function, and the third enthalpy, this is second, and this is the third Maxwell relation, and using Gibbs function we derive the fourth Maxwell relation. These equations are very important as per your exam.